Yeah, Prapti, we can start.
Okay, sir. Okay, sir. Everyone, my name is Prapti Tala, and I'm delighted to extend a warm welcome to each and every one of you to this invited talk on fascination of prime numbers. It's a privilege to see such a diverse and enthusiastic group of individuals gathered here today to explore one of the most captivating aspects of mathematics. Prime numbers have unique properties, and the mysteries they hold continue to spark our curiosity and inspire discoveries in various fields. Today, we have the opportunity to delve deep into the world of prime numbers, explore their significance, and appreciate the beauty that lies within these elusive integers. Moving forward, I would like to give a brief introduction about Curryleaf and introduce the speaker. Curryleaf is a math club of MTTS alumni whose name is motivated by famous Curryleaf trick, as Professor Gumbrason calls it, which is frequently a triangle inequality like arguments and analysis. The Curryleaf Club serves as a platform for MTTS alumni to make mathematics accessible to a larger group of people. In the spirit of MTTS, we regularly have invited talks by guest speakers along with other activities that aim to enlighten mathematics students. I would now like to introduce our speaker for today, Dr. Sudesh Khanduja. Dr. Sudesh Khanduja is an INSA senior scientist at IISER Mohali and an emeritus professor at the Center for Advanced Study in Mathematics at Punjab University. She completed her PhD in 1978 from Punjab University, and her current interests include algebraic number theory and valuation theory. She is a fellow of the World Academy of Sciences and has won numerous awards, including the Professor V.V. Narlikar Memorial Award of INSA in 2015. She has published numerous research papers, which have been published in the reputed international journals over the last 45 years. Professor Khanduja has been an invited speaker in many leading institutes in both India and abroad. We would now like to welcome Professor Khanduja to present a talk on the topic Fascination of Prime Numbers. Over to you, ma'am.
I'm thankful to the members of Curry Leaf Club for giving me a chance to give this lecture to an enthusiastic audience. And I'm also sorry for the mess, for the delay in not being able to get over to Zoom link. Now, I think I will start the lecture. One, two, three, 4, 5, 6. These are called numbers or natural numbers. Numbers are important not only for mathematicians, but generally they are important for all sciences and in everyday life. A number D is said to be a divisor or a factor of a number n if n is equal to d times m for some number m. For example, 6 is a factor of 18, 8 is a factor of 36, and 1 and n are always factor of any number n. Number theory is a branch of mathematics that is devoted primarily to the study of numbers and functions defined on the set of numbers. In the older term for number theory is arithmetic. German, and sometimes it's also called higher arithmetic. The first book which I studied on number theory was by Davenport, and it is called Higher Arithmetic. A German mathematician called Friedrich Gauss, this is a famous quote, almost all must have heard about it. Mathematics is the queen of all sciences, and number theory is the queen of mathematics, and prime numbers are at the core of all numbers. So, a prime number is a number greater than 1 strictly greater than 1, that has exactly two factors, 1 and itself. For example, 2, 3, 5, 7, 11, 13, these are first few prime numbers. A number which is strictly greater than 1 and not a prime is called a composite number. Uh, every number, even number except 2 is a composite number. Unfortunately, 1 is neither a prime nor a composite number. Prime numbers have fascinated mathematicians since eternity. I will just cite the quote of James Maynard, who won Fields Medal in July 2022. Quote, I personally find them totally fascinating. They feel they feel like some of the most basic and fundamental objects in mathematics. Unquote. Next slide. Next slide. I would like to tell about Fields Medal also. The Fields Medal is a prize given to 1, 2, or 3 or 4 mathematicians under 40 years of age at the International Congress of Mathematicians, a conference which is held at world level after every 4 years. The Fields Medal is regarded as one of the highest honors a mathematician can receive, and it has been described as the Nobel Prize of Mathematics. Though there are some basic differences like the frequency of the award, the criteria for the award, the age limit, and the monetary value. The name of the award is in honor of Canadian mathematician John Charles Fields. Charles Fields was instrumental in establishing the award, designing the medal himself. I will show you a facsimile of the medal. And he also took care of the monetary component. Till now, 64 mathematicians have received the Fields Medal. The first field medal were given to the first two Fields Medal were given in 1936 to Finnish mathematician Lars Alfors and American mathematician Jesse Douglas. In these 64 mathematicians, there have been only 2 women mathematicians. We will talk about them also. Next slide. This is the facsimile. You please try to explore. I'm talking about the students. Whose facsimile is this on the Fields Medal? Next slide. Primes are building blocks for numbers. Means that we are taught in schools that every number n greater than 1 can be expressed as a product of prime numbers. Nowadays, this is taught in school, and school children of 5th class are asked to factorize a given number into a product of numbers. And this is simple, like if n is a prime, nothing to prove, but if n is not prime, then n can be written as n1 times n2, where n1 and n2 are both less than n, greater than 1. If n1 is prime, let it stand, otherwise start factoring n1, and then start. After all, this process must end because all the factors we are getting are strictly less than n. And this factorization of n as a product of primes is unique in view of Euclid's first theorem. All of you must have heard of Euclid, the name Euclidean geometry. I will talk about Euclid in detail in the next slides. Next slide. Next slide. Euclid's first theorem. If P is a prime number and P divides a product AB of 2 numbers, then P divides at least one of them. And using this simple theorem, one can derive the fundamental theorem of arithmetic, that is, every positive integer greater than 1, every number greater than 1 can be represented as a product of 1 or 4 primes in exactly one way, except for the order of prime factors. That is, if n is equal to P1, P2, PR, product of P1, P2, PR, and n is also a product of Q1, Q2, QS, where all the PIs and all the QJs are primes, then R must be equal to S, and P1, P2, PR is a permutation of Q1, Q2, QR. Next slide. Prime factorization, let's do the prime factorization of the present year 2023. It's very exciting. 2023 is divisible by 7, and it's 7 multiplied by 289, and so its prime factorization is 7 multiplied by 17 square, and it is also expressible as 2 plus 0 plus 2 plus 3. This is 7, and it's 2 square 0 square sum of digits and sum of squares of digits. In the beginning of new year, my friend Professor Ajit Iqbal Singh, who is an accomplished mathematician based at Delhi University, sent me this poem. She writes very good poems on the spur of the moment. So on New Year, she says 7 days a week, because the prime number 7 occurs in it, with the excitement of a 7-year-old, with energy and enthusiasm of a 17-year-old. Let us all continue to do mathematics in any mode. And this is Professor Ajit Iqbal Singh. Next slide. Next slide. I will now talk about Euclid, because we said Euclid's first theorem. If P divides AB, then P divides either A or B. After conquering Greece, Asia Minor, and Egypt, Alexander the Great decided that he will build a capital city which will be the most magnificent in the whole world. So, and he conceived its name as Alexandria. And the city he built was no doubt first class, magnificent, but and he wanted to be center of education, but it was not immediately a center of higher education. It was after his death, when his half brother Ptolemy I ascended the throne of Egypt, that Alexandria became home to the world's first university. Because they had access to a big library containing more than 600,000 books, the library at Alexandria. And the first head of mathematics department was none other than Euclid. So that is the introduction. And Euclid, he lived between 323 BC to 283 BC, and he had a real passion besides numbers. He had a real passion for geometry. He wrote a series of books called Elements, a series of 13 books. First 6 books deal with two-dimensional geometry, and the last 3 books deal with solid geometry. And till the last century, Elements was the most selling book in the whole world after Bible. Although best known for his geometric results, Elements also includes various results in number theory. This is Euclid as we see in the paintings, and the quote written on it: "There is no royal road to geometry, but I will say there is no royal road to mathematics." Next slide. Next slide. Euclid's second theorem: the number of primes is infinite. I learned this theorem when I was in MSc first time, when I was in MSc part 2. And I will tell you from which book and who taught me. And the same proof I learned, because now when you open the internet, you will see dozens of proof of this theorem. The number of primes is infinite. The proof depends upon the fact that every natural number has a factorization into primes. Now assume that there is only a finite number of primes, and let's call them as P1, P2, Pm, and look at the number P1 multiplied by P2 multiplied by Pm and add 1 to the product. This number should also be written as a product of primes, and the primes have to come from P1, P2, Pm, but none of the PIs divide this number because every time the remainder 1 is left. So our assumption is wrong and there are infinitely many primes. Next slide, please. Next slide. So this is my teacher who first taught me number theory, and this is my PhD supervisor who taught me deeper number theory. The first elementary number theory was taught by him. Deeper number theory was taught by him, and he also suggested me to read a book on my own in the vacations of MSc Part 1, that book by Davenport, Higher Arithmetic, and that made me fall in love with number theory. So next slide, please. And this is my teacher who taught me algebraic number theory, and I wrote my when I wrote my book about a couple of years back, which has been published by Springer. I dedicated my book to him, to Professor R.P. Bamba. Next slide. There's a simple primality test. It is taught to school children also, or to my grandson when he was in 5th or 6th class. If a number n has no prime divisors less than or equal to under root n, then n is a prime number. Of course, those who study mathematics, they know the simple proof of it, because if n is not a prime number, n is equal to n1 times n2, and one of the where n1 and n2 are both greater than 1 and less than n. So one of either n1 or n2 will be less than or equal to under root n. Both cannot be strictly greater than under root n. And but n1 can say n1 is less than or equal to under root n. So, but n1 can be written as a product of primes, because every number we said can be written as a product of primes. So there will be a prime dividing n1, and that will be less than or equal to n1, and so it will be less than or equal to under root n as well. So let us look at the prime factorization of certain numbers, which is worth remembering for number theories. 1953. Of course, this is when we start factoring, we first see whether it's an even number. If it's an even number, it will be divisible by 2, but this is not an even number. But then we look at the sum of digits, that is 10, 15, 18, that's divisible by 3. So this number is divisible by 3. So it's 3, and when we divide it by 3, we get 651. And 651, again, the sum of the digits is divisible by 3, so it's divisible by 3. It's 3 into 217, and 217 is 7 multiplied by 31, and 7 and 31 are primes. And then 1974, this luckily is an even number, 2 multiplied by 987. And again, the sum of digits of 987 is divisible by 3. So factorizes as 3 multiplied by 329, and it is 7 multiplied by 47. And 1977 can be factorized as 3 multiplied by 659, and similarly 981 and 1984 is 2 raised per 6 multiplied by 31. And I've written a few names. So this is the birth year of Andrew Wiles, who is hero of the 20th century. He proved the long-standing problem of more than 350 years called Fermat's last theorem. He proved it. So I will talk about him in detail later. And this is the birth year of Manjul Bhargava, who also won a Fields Medal in 2014. Mariam Mirza Khani, who also won the Fields Medal in 2014, the first woman to win a Fields Medal. Akshay Vaktesh, Australian citizen but Indian origin, he won the Fields Medal in 2018. And Mariana Vyazovaska, second woman born in Ukraine to win the Fields Medal in 2022. Next slide. Mariam Mirza Khani was died at a very young age of 40 years, born on 12th May 1977, died on 14 July 2017, and her birthday 12th May is celebrated as International Women Mathematics Day throughout the world. And there are several quotes on the internet written by Mariam Mirza Khani, but I like this one the best. You have to spend, quote, you have to spend some energy and effort to see the beauty of maths, and mathematics really requires patience. Mathematics can't be learned in a hurry. It has its own logic, its own path. So this really fits into the situation. Next slide, please. Manjul Bhargava is a number theorist. That's a matter of great pleasure for us. Next slide. Akshay Vaktesh also works in number theory. Next slide. These are the field medalists of 2022. Mariana Vyazovska, then James Maynard. Well, he works in analytic number theory. She works more towards geometry of numbers. Then John Hugh, then Dominil Cumin. Next slide, please. Next slide. Dirichlet's theorem. There's a famous theorem which has also connection with primes. There are infinitely many primes in any arithmetic progression: a plus b, a plus 2b, a plus 3b. If the first term a and the common difference b have no common factor, if they accept one, if their GCD is 1, if GCD of a and b is 1, then this infinite arithmetic progression contains infinitely many primes. And this theorem was first conjectured by Gauss, and it was proved by Dirichlet in 1837. Dirichlet's theorem tells us, as a simple application of Dirichlet's theorem, it tells us that there are infinitely many prime numbers ending in the number 99, because one can consider a equal to 99, b equal to 100. So the series will be 99 plus 100 plus 99 plus b equal to 100, a equal to 99. So 99 plus 99 plus 100 plus 99 plus 200 plus 99 plus 300 plus so on. And so this series will contain infinitely many prime numbers. And so there will be infinitely many primes whose last two digits will be 99. And there is no problem. There will be infinitely many primes by the same argument whose last three digits will be 999. And you can extend your imagination. And there will be infinitely many primes whose last four digits are 9999. Similar argument. So an application of Dirichlet's theorem. For in the first course in number theory, this theorem is taught. Of course, this is taught in the second semester. This is taught in the first semester course on number theory. For every number n strictly greater than 1, there is a prime line between n and 2n. Means there's a prime line between 2 and 4. Of course, 3 is prime line between 2 and 4. There's a prime line between 3 and 6. Of course, there may be more than one prime between 3 and 6. And between 4 and 8, 5 and 7 are the two primes line. And this was conjectured by Bertrand in 1845 and proved by Chebyshev in 1852. Chebyshev was a student of Bertrand. Next slide. Sometimes students over smart teachers, and it's a it happens many times in history. Twin primes. Twin primes are pairs of primes which differ by 2. History says this name was coined by Steckel in 1816. The first few primes are 3, 5, twin primes are 3, 5, 5, 7, 11, 13, 17, 19, 29, 31. Then one can think of 59, 61 and many other pairs. Conjecture is there are infinitely many twin primes. And numerical evidence leads us to suspect an affirmative conclusion. Using electronic computers, 808 trillion, 675 billion, 888 million, 577,436 pairs of twin primes less than 10 raised by 18 have been discovered. Many immense examples of twin primes are known. The largest pair of twin primes known till today is 2 trillion 996 billion 866 million 34,895 multiplied by 2 raised per 1 million to 290,000, and one prime is with -1 here, another prime will be with a +1 with this number because the difference is 2, and each of these two primes have 388,342 decimal digits in it. For example, the prime 3 has 1 decimal digit, the 13 has 2 decimal digits, and 1,297 has 4 decimal digits, but each of these primes have more than 388,000 decimal digits. And this pair of twin primes was discovered in September 2016. Next slide, please. I will tell something very interesting and easy to understand results of James Maynard, who's a field medalist of 2022 result on primes. In May 2013, Yitang Zhang, a mathematician based at an American university, proved that there are infinitely many prime pairs, because they cannot prove there are infinitely many primes with gap 2. So what he proved was that there are infinitely many prime pairs with gap up to 70 million. That is the difference between two primes in a pair was less than or equal to 70 million. And for this, imagine for this, Zhang was given several prizes. In 2013, he won the Ostrowski Prize of American Math Society. In 2014, he was given the Kaur Prize in Number Theory by American Math Society. And 2014, he was an invited speaker at the International Congress of Mathematicians held in South Korea, Seoul. So in November 2013, James Maynard proved that there are 50 many prime pairs with gap less than or equal to 600. From 70 million, he squeezed the gap to 600. In April 2014, this gap was narrowed down to 246 by Polymath Project 8, in which he was also a party. James Maynard was a party. And actually, Polymath Math Project is a collaboration between a group of mathematicians who work together for best solution of a problem. Maynard showed that not only do we get pairs of primes coming close together, but we get clusters of many primes coming close. And the theorem one of the theorems he proved is the following. In 2014, for each natural number m greater than or equal to 2, there exists a positive integer cm with the following property. There are infinitely many natural numbers n such that the interval n comma n plus cm contains at least m prime numbers. It contains n comma n plus cm contains at least m prime numbers, and we want if there are infinitely many twin primes, then m will be 1, and cm we want to be 2. cm we want to be 2. And one of the very next interesting result James Maynard proved is that there are a infinite number of primes that do not have the digit 7 in them. In fact, he proved that you fix any digit between 1, 2, 3, 4, 5, 6, 7, 8, 9. There will be infinitely many primes. We do not have that particular digit. Next slide. Next slide. Mersenne primes. It has been traditional to call primes of the form m sub n equal to m sub n we denote by 2 raised by n minus 1. So primes of the form which can be written 2 raised by n minus 1 Mersenne primes after a French monk Marin Mersenne, best known as a priest scientist. He was a priest in a church. Note that 2 raised by m for any number m and s, 2 raised by m minus 1 divides 2 raised by ms minus 1, because we can write 2 raised by ms minus 1 as 2 raised by m minus 1 into 2 raised by m into s minus 1. Simple this thing. Now, if m sub n equal to 2 raised by n minus 1 is a prime number, then the above equation shows that n must be a prime number. But in 1536, Regius proved that 2 raised by 11 minus 1 is not a prime number. So the converse is not true. If m sub n is a prime number, then n must be a prime number. But if p is a prime number, then 2 raised by p minus 1 may not be a prime. In 1644, Mersenne wrote in his book Physica Mathematica that m sub p is a prime for p equal to 2, 3, 5, 7, 13, 17, 19, 13, these, and composite for other numbers less than 257. The statement contained 5 omissions and errors, and it took 3 centuries for mathematicians to correct his claim. It is now known that M67 and M257 are not primes, but M61, M89, and M107 are primes. And why Mersenne primes? Every book contains reference to Mersenne primes and a study of many Mersenne primes. I will not have time to talk about perfect numbers. Mersenne primes have a very close connection with perfect numbers. Perfect number is a number, some of whose divisors except the number, some of all whose divisors which are less than n adds up to n. So actually Mersenne did a lot to promote number theory. He used to teach nuns and monks in the church mathematics, number theory, and they used to write letters, collaborate with other mathematicians, including one very famous mathematician about which I will talk in the next few slides. When Mersenne died, in his room were found stacks of letters in which were written by 78 different mathematicians. Next slide. Next slide. Till now, 51 Mersenne primes are known. The largest known Mersenne prime as of December 7, 2018 is 2 raised by 82,589,933 minus 1, which has 24,862,048 decimal digits. This prime was discovered by Patrick Laroche as part of the Great Internet Mersenne Prime Search Project. The 25th and 26th primes were found by 2 school students, Laura Nicken and Landon Courtnall, in 1978. And these primes had more than 6,500 digits, each of them. This discovery made a national television news and front page of all leading newspapers in the world because the 2 school students found this Mersenne prime. Next slide, please. Prime numbers have fascinated medical professionals also, not only mathematicians. A Mersenne prime was discovered by Martin Nowak, a German eye specialist with a passion for mathematics. His prime number revealed in February 2005 had more than 7,080,000 digits. According to researchers, quote, people ask us why we do this. It is like going on a quest. We are looking for something incredibly rare. This pushes the computer scientists to develop algorithms that run highly efficiently. Unquote. In 2008, Electronic Frontier Foundation gave an award of $100,000 to the Department of Mathematics, University of California, Los Angeles, for finding the first Mersenne prime with more than 10 million digits. And young students, 2 computing awards are up your grabs. Pay attention, 2 computing awards are still up for grabs. Electronic Frontier Foundation will award $150,000 to the first individual or group who discovers a prime with at least 100 million digits, and an award of $250,000 for a person or a group for finding a prime with at least 1 billion digits. Next slide. Prime numbers have many uses. Prime numbers and cryptography. Every time you buy something on the internet with a credit card, you are indirectly using prime numbers to keep your personal information secure. How? Using cryptography. Cryptography is the study of methods for sending messages in secret so that only the intended recipient can remove the disguise and read the message or decipher it. RSA Revest Shamir Adilman is a public key crypto system that is widely used for secure data transformation. And now, of course, there are many more discoveries. The acronym RSA comes from the surnames of Ron Rivest, Adi Shamir, and Leonard Edelman, who publicly described the algorithm in 1977. This is one of the most popular algorithms. Next slide. Ron Rivest, Adi Shamir, and Leonard Edelman, this is their photograph when they discovered it in 1977. Of course, now they are much senior people. Next slide. I will not talk about RSA crypto system. Next slide. Sums of 2 squares. Note that for all numbers a and b, a square, simple formula, a square minus b square whole square plus 2ab whole square equal to a square plus b square whole square. And substituting a equal to 2b equal to 1, you get 3 square plus 4 square equal to 5 square. Similarly, substituting a equal to 3, b equal to 2, you get 5 square plus 12 square equal to 13 square, and giving different values to a and b, you have infinitely many triplets like this, which satisfy a square minus b square. A square which satisfy sum of 2 squares is another square. So it is impossible to write infinitely many squares as sums of 2 squares. These are also called Pythagorean triples. So in 1637, Pierre de Fermat, I'll talk about him, made the following conjecture. Conjecture is a result which is strongly felt it is true, but the proof is not available. But it is strongly felt that it is true. Fermat's last theorem it is impossible, but since now it is known, so I call it theorem now. At that time it was a conjecture. It is impossible to write a cube as a sum of two cubes, a fourth power as a sum of two fourth powers, or in general any power beyond the second as a sum of two similar powers. You cannot write a cube plus b cube equal to c cube for non-zero integers a, b, c, and similarly for fourth power, and similarly for any power strictly greater than 2. Next slide, please. So this is a face of Pierre de Fermat, and this is the cover page of book called Fermat's last theorem, the conjecture which I just mentioned, the book written by Simon Singh. Next slide. I will talk a little bit about Pierre de Fermat. Fermat was born on August 1601 in the town of Beaumont-de-Lomagne in southwest France. His father was a wealthy leather merchant, so he was fortunate to study in a good school, and after a stint at the University of Toulouse, he joined law at Orleans. Like all Indian parents, his parents wanted him to join civil services. So like most Indian parents wanted him to join civil services. So his family steered Fermat towards a career in civil service. So by 1631, at the age of 30, Fermat was a magistrate and a councillor at the Chamber of Petitions at Toulouse. His job was to listen to the complaints against the king. So Fermat did filed by public. So Fermat did mathematics as a hobby in his leisure time. Yet he contributed a lot to the advancement of the subject. Next slide. He is considered to be one of the inventors of analytic geometry. He also laid technical foundations of differential and integral calculus. For years, it was thought that Newton laid the foundation of integral calculus on his own. But in 1934, Louis Moore discovered a note which put the record straight. Newton wrote that he based his calculus on Monsieur Fermat's method of drawing tangents, and Fermat with Pascal established the conceptual guidelines of the theory of probability. But Fermat is best known for his work in number theory, in particular for Fermat's last theorem. And this theorem states, earlier I've also stated it, is saying that you cannot write a cube as a sum of two cubes, a fourth power as a sum of two fourth powers, and so on and so forth for higher powers. But mathematician will state it's the equation x to the power n plus y to the power n equal to z to the power n has no solution in non-zero integers x, y, z, where n is strictly greater than 2. And Fermat himself proved the case n equal to 4 of the theorem. Over the years, Fermat's last theorem was proved for specific values of n. History reveals that in 1770, Leonhard Euler, one of the brightest Swiss mathematicians, used the field q omega, where omega is a complex cube root of unity, to prove this theorem for n equal to 3. This is almost 100 years after the death of Fermat, that Leonhard Euler could prove the case n equal to 3 of the theorem. Next slide. Next slide. If n equal to p times m, then the relation p is a prime number and m is a positive integer. Then the relation x to the power n plus y to the power m equal to z to the power n implies that xm whole to the power p plus y to the power m whole is equal to z to the power, which gives a solution to the equation x to the power p plus y to the power p equal to z to the power p. Since any integer strictly greater than 2 is either a multiple of 4 or is an odd prime factor, so it remains for proving Fermat's last theorem, it remains to be shown that x to the power p plus y to the power p equal to z to the power p has no solution in non-zero integers for all odd primes p, because Fermat himself had proved it for the case n equal 4. This celebrated theorem motivated the origin of algebraic number theory. Simon Singh, who's in his book Fermat's Last Theorem, whose photo I've already shown to you, whose cover page photo I've already shown to you, takes us through a journey of the struggle of the math world for more than 350 years to prove this theorem. And I recommend every college has a copy of should have a copy of Simon Singh's book. It's an inspiring account of this theorem, written as in the form of a novel. Next slide, but giving complete information. Sophie Germain, the first major step towards a general proof of Fermat's last theorem was by a French woman, Sophie Germain. Remember why I have used the word woman, because Sophie Germain was not allowed, women at that time were not allowed to join a college or a university. And Sophie Germain, under the pseudonym Monsieur Leblanc, under the false name Monsieur Leblanc, joined L'École Polytechnique, which was opened in Paris when she was 18 years old. And she used to obtain class notes under the name Monsieur Leblanc. But the supervisor of the course was Just Lagrange, and he could not ignore the brilliance of Monsieur Leblanc's exercise notes. So he sought a meeting with Mr. Leblanc, and Sophie Germain was forced to reveal her identity. And after that, Lagrange became her mentor and introduced her to the greatest number theorist of that time, Carl Friedrich Gauss. So in a letter dated May 12, 1819 to Carl Friedrich Gauss, Sophie Germain explained her idea of the first step towards a general proof of Fermat's last theorem. Let P be an odd prime such that Q equal to 2K plus P is also a prime for some number K such that the following conditions are satisfied. Number one, x to the power P is equal to P mod Q has no solution. The set of pth powers modulo Q contains no consecutive non-zero integers. Then the equation x to the power P plus y equal to z to the power P has no solution in integers x, y, z, with P not dividing the product x, y, z. This is in literature referred to as the first case of Fermat's last theorem, saying that no solution in integers x, y, z with P not dividing x, y, z. In particular, one can verify that if P and 2P plus 1 are odd primes like 3 and 7, then the first case of Fermat's last theorem, these two conditions are satisfied, and therefore the first case of Fermat's last theorem holds for the exponent P. Next slide, please. Next slide. This is Sophie Germain. Next slide. This is Carl Friedrich Gauss, called the Prince of Mathematicians. Next slide. In this way, Sophie Germain was able to show that the first case of Fermat's last theorem holds for all primes less than or equal to 197. In 1825, her method claimed its first complete success when famous mathematician Dirichlet, whose theorem I stated, and Alexander, working independently, one from Germany, other from France, were able to prove the case P equal to 5 of Fermat's last theorem. 14 years later, in 1839, French mathematician Gabriel Lame proved the case P equal to 7 using Germain's results. Her results related to Fermat's last theorem remained most important until the contribution of Edward Kummer in 1947. Next slide, please. So the German mathematician Edward Kummer contributed a lot towards this subject. While you study number theory, you will learn that the concept of an ideal of a ring was born in the work of Kummer and Dedekind. By using theory of ideals, Kummer proved Fermat's last theorem for a wide range of prime exponents called regular primes. Attempts to prove the theorem led to the discovery of algebraic number theory and a wealth of other mathematical discoveries. The theory now has applications to several topics in mathematics. It is this wider link that led to the final complete proof of Fermat's last theorem by Andrew Wiles, whose birth year I mentioned already, 1953. Next slide, please. Next slide. So this is Kummer from 1810 to 1893. Next slide. In 1963, Andrew Wiles, in 1963, a 10-year-old boy sitting in the Milton Road Library in Cambridge Cambridge, read the statement of Fermat's last theorem in E.T. Bell's book, The Last Problem. He was born in Cambridge, studied in Cambridge, did his PhD in Cambridge. He was fascinated by this simple-looking problem. Quote, I knew from the moment that I would never let it go. I had to solve it. Andrew Wiles revealed when he was able to solve it. After 30 years of dreaming and 7 years of single-minded efforts, Wiles completed a proof of Fermat's last theorem in May 1993, because it was in 1963 when he first, sitting in the Milton Road Library, he read the statement of Fermat's last theorem. He outlined the proof in 3 lectures in a conference held at Sir Isaac Newton Institute in Cambridge in June 1993. At the end of his 3rd lecture, when he concluded Fermat's last theorem, he became the most famous mathematician in the world. Next slide. So this is Andrew Wiles as he looks today. At that time, he was very young. Next slide. In the words of Cambridge Professor John Kaur, who was PhD supervisor of Andrew Wiles, quote, a proof of Fermat's last theorem is a great intellectual triumph, and one shouldn't lose sight of the fact that it has revolutionized number theory in one fell swoop. For me, the charm and beauty of Andrew's work is that it has been a tremendous step towards algebraic number theory. Unquote. Next slide. I will, for the sake of students, I will just tell one simple mathematical problem, which is as important as, which is no less than important than Fermat's last theorem, mathematical mystery, Goldbach conjecture. Even though Wiles has disposed of the most famous problem in number theory, there is still a multitude of unsolved mathematical conundrums. One number theory problem dates back to June 7, 1742, when Christian Goldbach, tutor to the Tsar of Russia, wrote a letter to the great Swiss mathematician Leonhard Euler. Goldbach had examined dozens of even numbers and noticed that they could all be split as a sum of 2 primes. Like 8 can be written as 3 plus 5, and 10 can be written as 5 plus 5, 3 plus 7, and so on and so forth. Next slide, please. So Goldbach's conjecture says every even number greater than or equal to 4 can be written as a sum of 2 primes. Goldbach conjecture has been verified for even numbers up to 4 multiplied by 10 raised by 18 using computers. But it has not been proved for any n, for any even number greater than or equal to, for all even numbers greater than or equal to 4. But there is Goldbach's weak conjecture, is called the ternary Goldbach conjecture. It says that every odd number n greater than or equal to 7 is a sum of 3 primes. Goldbach's conjecture implies Goldbach's weak conjecture, because if n greater than or equal to 7 is odd, then n minus 3 is even, and n minus 3 can be written as a sum of 2 primes. So n can be written as a sum of 3 primes. Next slide. In 1941, Stalin, Russian king, gave a prize of 100,000 rubles to the Russian mathematician Vinogradov, who proved Goldbach's weak conjecture holds for sufficiently large and greater than equal to 3.25 multiplied by 10 rows per 60 something number greater than 68 million. In 2014, Harold Anders Helfgott from Paris posted a manuscript of 133 pages proving the ternary Goldbach conjecture. And I attended his lecture in 2014 in the International Congress of Mathematicians held in Seoul. Next slide, please. So this is a relatively young person. And next slide, please. Next slide. Who proved ternary Goldbach weak conjecture. Mathematics, a young man's game. The Cambridge professor G.H. Hardy, in his book A Mathematician's Apology, has written, quote, "No mathematician should ever forget that mathematics, more than any other art or science, is a young man's game. To take a simple illustration, the average age of election to Royal Society is lowest in mathematics. His own most brilliant collaborator, Srinivas Ramanujan, was elected as Fellow of the Royal Society at the age of just 31, having made a series of outstanding breakthroughs during his youth. Despite having received very little formal education in his hometown of Kumbakonam near Madras, Ramanujan was able to create theorems and solutions which had evaded mathematicians in the West. When he posted his results to Hardy, the Cambridge professor was so impressed that he invited him to attend Trinity College and leave his job as a clerk in Madras Post Trust. Next slide, please. Next slide. So this is Ramanujan, who had a short life of hardly 33 years. Next slide. Do I have how much time I have? Do I have 10 more minutes, 5 more minutes?
Sure, ma'am, sure.
I will talk only about Ramanujan's work on highly composite numbers. Ramanujan's, because these also are concerned prime numbers. Ramanujan's most important work done during the first year of his reaching in Cambridge appeared in Proceedings of the London Mathematical Society in the year 1915. A number n is called a highly composite number if it has more divisors than any number smaller than n. That is, the number of divisors of n is strictly greater than the number of divisors of n dash, where n dash is a number smaller than, where n dash is any number smaller than n. Ramanujan explored the properties of highly composite numbers and listed about 100 highly composite numbers. The first few are 2, 4, 6, 12. The prime factorization of any composite number, Ramanujan proved the prime factorization of any composite number n can be written in the form n equal to 2 raised by a2 multiplied by 2 raised by a3 multiplied by 5 raised by a5, finite a product multiplied 7 raised by Ramanujan proved that if n is a highly composite number, then all these indices, all these exponents, sorry, not indices, exponents a2, a3, a5, a7 will be positive, and they will form a decreasing sequence. And he showed that with two exceptions, 4 and 36, the last non-zero AP was always 1, because for 4 it is 2 multiplied 2 square, so it is even, and in 36 it is 2 square multiplied by 3 square, so there also it is 2. If qx is the number of highly composite numbers less than or equal to x, Ramanujan showed that limit x tending to infinity qx divided by log x is infinity. This really has impressed me. And just yesterday, one of my colleagues, Yashonidhi Pandey, he gave me a book written by Rons Ross Honsberger, Mathematical Gems, Part 1, Part 2, Part 3. And in Part 3, the proof of very simple proof of this fact is given. Maybe the same proof as Ramanujan gave, or maybe slightly different proof, that these AIs are decreasing. And with the two exceptions, AP is always 1, and also this limit is infinity. Next slide. In the words of Professor G.H. Hardy, Cambridge Professor G.H. Hardy, quote, the problem Ramanujan has addressed is very peculiar one, standing somewhat apart from the main channels of mathematical research. But there can be no question as to the extraordinary insight and ingenuity which he has shown in treating it, nor any doubt that his memoir is one of the most remarkable published in England for many years. Unquote. Years later, Hardy would contrive an informal scale of natural mathematical ability, on which Hardy assigned himself a scale of a grade of 25, and Littlewood a grade of 30. To David Hilbert, the most eminent mathematicians of his day, Hardy assigned grade of 80, and to Ramanujan he gave 100. So that was the brilliance of Ramanujan. Next slide. I will end the lecture with a quote by Paul Erdős, 20th century mathematician. It will be another million years at least before we understand the primes. Next slide. Here are the references. This is Ramanujan's biography written by Robert Cunningham, The Man Who Knew Infinity, from which I took several quotes. Simon Singh's book, Fermat's Last Theorem. Helf got a reference to his proof of Goldbach-Weak conjecture. Zhang paper's reference in which he said that there are infinitely many prime pairs with gap less than or equal to 70 million, and James Maynard work on prime numbers. And this is the first book that made me fall in love with number theory by Davenport, The Higher Arithmetic, an Introduction to the Theory of Numbers, Cambridge University Press. I studied the second edition, which was printed somewhere in 1970s. Now this reprint, the reprint which is available is reprinted in 2020, and at the 8th edition of the book. And if one wants to read number theory just like in novel, one wants to know something about number theory, one should read this book by Davenport. Next slide. This is a reference of my own book, which I dedicated to my teacher who taught me algebraic number theory, Professor R.P. Bamba, whose 98th birthday falls after 2 days on 30th of September. I wish I could dedicate this lecture to him had it been on 30th of September, but that was a Sunday. And the last reference which I could not add is that of Ross Honsberger, Mathematical Gems, Part 1, Part 2, Part 3, about which my colleague Yashunidhi Pandey told me yesterday evening. So, and now, finally, thank you very much for your patience.
Thanks a lot, ma'am. As we come close to this enlightening invited talk, I would like to thank you for giving such a wonderful talk. I would also like to thank everyone who attended this seminar for their active participation and enthusiasm. I'm sure all of us got to learn a lot of new stuff at this talk today, and we are delighted that we had the opportunity to do so. Thank you, ma'am.
Somebody is raising a hand, I suppose.
Yeah, Alapan.
Somebody
Yes,
is
ma'am.
raising,
Yes.
somebody is raising a hand. Alapan Ghosh. Yes, Alapan.
Yes, ma'am. I had a question that, ma'am, the work of Terence Tao and Green, their work on twine primes, like how much they have done or what they have done in.
I'm not aware of their work. I only read about James Maynard work. Actually, to tell you the truth, because I don't really work in analytic number theory, and this is more towards analytic number theory. But you can. So I'm not working in analytics number. I have not read about the work. I only read about James Maynard work because some of his results were strikingly simple to look at, though they had very hard proofs.
Ma'am, what is the motivation for you to study number theory?
Well, I uh, 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 for me, I told you that while I had my exams of MSc Part 1 were over, and MSc and there were vacations, like after annual exams there used to be vacations of 2 months, and so I went to one of my teachers and I asked him, I want to during these vacations I want to read some book which I can read on my own just as a novel, which relaxes me, and which also by which I feel relaxed, and of course I learned something new also. Then my teacher, Professor Indras Luther, he told me that you can have the book of, you can read the book of Davenport, a course in higher arithmetic. So that was the title of the book. So I think I got that book issued from the library, from our library, and I took it home. And as I kept on reading it, there were no big theorems, but there was so much basic things, and they were explained in such a nice manner that everything, uh, captivated me, and everything captivated me. And then I was promoted to MSc Part 2. I joined back the institute, and there were our three subjects were compulsory, and there was an option between number theory course and statistics course, and the whole class took up statistics because statistics at that time, it was very fashionable to study statistics because people thought that they will get jobs, immediate jobs in banks, and they will get they'll get to IRS Indian Revenue Service, and so on and so forth. And the whole class took up statistics. Only 3 failures who had failed already in MSc Part 2 only, and they had studied number theory and they had not studied statistics because it was a newly introduced option. So only though they took up statistics, only they took up number theory, and I also took up statistics. I thought, why to take up number theory? Because everybody, I will also follow the crowd. So, and in this way, 2 months passed, and we had a very brilliant statistics teacher. His name was J.V. Deshpande, done PhD from University of Oxford, and he gave me extra time. I also bought the book of Hogg and Cragg, and he did his best to make me interested in probability. That first chapter he taught was probability, and I sat in the class. Every time my mind went back to the beautiful results that I had seen in that book, how exact everything was, how beautifully it was explained, and how and here everything is a little vague. Probability, everything. So my heart lay with number theory, my body was in the class of statistics. So 2 months passed, and ultimately I decided that I cannot go with the statistics class, in spite of the best help of my teacher, Professor Pandey. I requested the teacher who was teaching number theory, and already I was late by 2 months, Professor Nanda. I requested him that I want to come to number theory. Will you let me join? He told me that I have covered so much syllabus, you have to cover, you have to read on your own. So I wrote notes on my own, and then I was soon with the class, and then there was no looking back. So I did my PhD in a subject which was also closely related to number theory, though it was very difficult kind of thing. And then my students, several of my students wrote their thesis in algebraic number theory. Some wrote their thesis in valuation theory, because valuation theory is a good sound knowledge of valuation theory is essential to know algebraic number theory. So that is it.
Yeah. Yes, ma'am. Thank you, ma'am.
Yeah, Haripriya.
Yeah, ma'am. First of all, it is a really great lecture from your part, and thank you so much. And I want to ask you something like, if I supposed to do a last year project on prime numbers, then what all the topics I can include to make it a good project report?
If you want to make a, you want to make a
Final year project report. Project, ma'am.
It just depends upon your taste. There are very good theorems that there are new and new better and better versions of prime number theorem also, like this year only, while I was writing a paper from an analytic number theorist, I came to know a very good version of prime number theorem. Prime number, the number of primes less than or equal to x. We as a student learned only the asymptotic formula. It's asymptotic to x upon log x, you know? but there are very good bounds that pi x lies between the two bounds, and they're very good constants, and they're newer and newer techniques and newer constants. So that just depends upon your interest. That just depends upon your interest and your level of depth of level of knowledge, you know, and your how much you want to delve into number theory. So there's no end to learning about prime numbers. Yes, the last quote said that it'll be another million years before we know the primes. So that really speaks about the depth of the study of prime numbers. How much time we have, how much attention we want to pay, how much knowledge we have. So that is it. How much we want to work on certain thing, how much time we want to devote to certain thing. It just depends upon that.
Yes, ma'am. Thank you so much.
Supratim.
Yes, yes, sir. Hello, ma'am.
Hanji, Supritam.
I have a question about number in mathematics. Mathematics means and the subject is used to count something. Here in number theory, I have nurtured a phobia about number theory as I I can little bit problem in doing calculation like arithmetic operation, multiplication or addition, subtraction. I need some time, and in every step I face some problem in my mind that I cannot calculate number so easily. Then how can I study number theory, or and
No,
how
you
can
don't
I?
have to calculate. You don't have to calculate. You don't have to calculate. In number theory, not all number theory is based on calculations. Calculations nowadays are done by computers. No. Mathematics, number theory is like one of the very good theorems of number theory is for any number A, co-prime with P, A raised to power P minus 1 is A raised to power P is congruent to A mod P. No?
Yes,
So,
yes.
so using this little, you can sometimes find the last digit in A to the power B or something like this. No? So it's just application of little things. You don't have to do calculations with hands. Number theory is not calculations. Calculations of number, multiplying them or dividing them. That is not number theory.
Uh,
Number theory is the art of working with numbers, playing with numbers. Okay.
there is no connection, logical, no connection in
Is
between them.
it is understanding the laws of numbers. It's understanding the laws which numbers enjoy, the
Yes,
properties which numbers enjoy, the properties which various kinds of numbers enjoy. That is a theory of numbers. Okay. It's not that you should be able to faster multiply it. I think I will be the slowest. My grandson can quickly multiply two numbers, then I can. But he doesn't know. But he doesn't know the laws of number theory. No.
yes,
He can quickly verify whether a number is divisible by 3 or whether a number is divisible by 9. But he doesn't know that if the sum of the digits is divisible by 9, then why should the number be divisible by 9? That argument he doesn't know. No, because he's just like a mechanic. He knows how to, you understand, he knows how to apply the rule. But how the rule is proved, that is learning to prove the rule is studying theory. Okay.
yes, yes, ma'am.
Phobia, you will get over if you read a book like the one I mentioned.
Uh, uh, okay.
Okay.
Actually, ma'am, I am diagnosed with some anxiety norms medically. So so some kind of intrusive thought comes in my mind about I am a student of mathematics master's class. So I asked about that.
What I said, does it answer your question?
Yes, ma'am.
Whatever I said, does it answer your question?
Yes, ma'am.
Okay.
Yeah.
And it's not that everybody will like everything. Like I could not like, after my hard efforts, after 2 months of attending the class, I could not like statistics. That doesn't mean that nobody likes statistics or statistics has no use. It's just that what you follow your passion, what you like
Yeah.
best, you follow that. And everybody has different passions.
Yes, ma'am. Thank you.
Excellent.
Professor Ajit Iqbal Singh is here. Hello, ma'am.
Yes. Yes, Professor Jeet Gal Singh, of course, she was there.
Yes,
Hello. Hello, ma'am. How are you?
I'm very much there. Fascinating talk and fascinating interaction is going on. Everybody is learning a lot, and I'm the most enthusiastic person from that lot. Thank you very much.
Thank you for attending the talk.
Okay.
Gaurav.
Gaurav Mishra.
Good evening, ma'am.
Good evening, Gaurav.
And that was so nice of you, ma'am. Ma'am, I want to know ki I'm a beginner in number theory. What are the prerequisites for studying algebraic number theory or understanding algebraic number theory?
What are the
Prerequisite for understanding algebraic number theory, ma'am.
you should have a basic knowledge of algebra, means groups, rings, and field theory. Okay, and also Galois theory.
Ma'am, basically, it's the abstract algebra section, no?
Yes, you are right. Okay, and then also number theory, because when you study, you should know about numbers, that there are infinitely many prime numbers. Then you will enjoy studying prime ideals. So elementary number theory you should know, like Naive and Zuckerman stuff. Okay, and you should
Okay,
know
ma'am.
so that's all you need to know.
Okay, ma'am. Thank you so much, ma'am.
Alapan Ghosh wants to ask something.
Yeah, ma'am. Again, ma'am, just like for Goldberg conjecture, this what
Goldbach conjecture, yes.
Goldberg conjecture. What would be its possible applications, or is there any, I mean, advancement through it towards its application?
The people have derived certain results, but they are just related theoretical results. I don't know which kind of applications, but theoretical results are there. You read more in detail about. There are certain weaker forms. One weaker form I talked about. There are other weaker forms also. So that kind of fit is there, and certain things I tell you are just challenges, and they are done for fun. Okay, they're just done for fun also, in the sense that later on there come out to be uses of it. Later on there come out to be uses of it. First of all, everybody made fun of mathematicians. What is the use of finding such large prime numbers? And now you know that they are being used in cryptography. You know? So certain things are discovered as it is on the face of it. People later on find applications to it.
Yeah.
Those who discover, they may not find applications of it. Those who use, those later on people can sometimes find applications.
Thank you, ma'am.
Welcome.
Yeah. Ma'am, can we have a group photo with you?
Yes, why not?
So I would request all of the audience to please switch on their videos. I'll wait for a few seconds so that everyone opens their videos. Great. Almost all of you have opened. Ready? Okay, one more. Thank you. Yeah, Prapti, over to you.
Yes, sir. Okay. Thank you so much, ma'am, for agreeing to do this interview with us. We are very eager and excited to hear from you. So my first question is, could you please tell us a brief about your journey in mathematics and what motivated you to pursue a research career in mathematics?
Actually, to tell you the truth, it was very different. In my case, I was the smallest, youngest among the 7 brothers and sisters of my family who had migrated from Pakistan. So, we settled, and all our properties and belongings were left in Pakistan. So the government gave us a big house in a village very close to Ambala city. So so my parents thought that she will do BA, and we'll get a good match and we will marry her off. And so with this purpose, they said, okay, you can study till BA. But then I topped in the university in BA Part 1, Part 2, and Part 3. Punjab University at that time was very big. Kurukshetra University didn't exist. Himachal University was also a part of Punjab University. So that was undivided Punjab at that time. Haryana did not exist. So I then they said, okay, since you are getting such a great scholarship, you can go to Chandigarh for doing MA in mathematics. That time mathematics in Punjab University was called MA in mathematics. So I got admission there. And there I met very brilliant teachers. They had done from PhD from had done PhD from abroad. Professor R.P. Bamba was the head. Our teachers were Professor Rajinder Rijit. There was only one lady teacher. She had also done PhD from abroad, Ohio State University, Columbus. And then we had very brilliant teachers. And then my own, later on, our teacher, Professor Inder S. Luther, who later on became my PhD guide. He was also PhD from Illinois, Urbana champion. And we had a team of brilliant students. It was a center for advanced study in mathematics. And looking at them, looking at their scholarly atmosphere, I had a desire to do PhD in mathematics. And my parents at that time had shed their fears, because I was the first girl to go and study and start out of the house and stay in a hostel in a different city in Chandigarh. So by that time things changed, their viewpoint changed, and I did PhD in mathematics. and then I got a job there only, a permanent faculty post in that very department. And that is how the journey began. And of course, the journey had its, when I got married, I had this, my husband was very busy. He was in a hospital working from morning till evening. So, and there was nobody from the family to help me looking after the child. So there was a break in my career. Also, then we had a teacher, Professor R.P. Bamba, whose photograph I showed you. Then he was the vice chancellor of the university at that time. So he was also on the governing body of the hospital where my husband worked. It was a government institute, postgraduate institute of medical education and research, Chandigarh. So then he looked at the annual report of the PGI, my husband's hospital, and he said, "Oh, your husband has written 5 papers in 1 year, and during the last 5 years, you have not written a single paper." And that comment, that sort of changed my path. And I determined that I will not lag behind my husband. And slowly and steadily, I overcame the gap. And then I was very lucky in students also. I got I got supportive parents. I got very dedicated students. When I was head of department for 3 years, for several years, I was also coordinator, Center for Advanced Study in Mathematics. There was a lot of administrative work to be done. And the whole day I will be busy with the official work. So the research students will come to my house, both of us will sit on a carpet and sit together for hours together and work. And they had the patience to adjust with me. They had the patience to adjust with my timings, because department work was also necessary, and their PhD work, and they produced very good work. All of them were dedicated to and very adjusting according to my time. So it was, I was lucky both in parents, teachers, and students, as well as, of course, my husband and children also, because they had to bear that loneliness when I was busy with the students. My children, I asked them, they will stay upstairs, and because my students get disturbed when they come downstairs. So it was cooperation of all of them which helped me to go through this journey, hard journey.
Ma'am, could you tell us a little bit about your research so that we could understand?
It's very difficult to explain any research result, to be frank. But I will say my research centers around algebraic number theory. And of course, I use a lot of valuation theory also. And I extended certain classical results of algebraic number theory, like Dedekind's theorem on splitting up primes, which you read in your first course in algebraic number theory. That's all I will say, because it will require a lot of notations, a lot of setup to say the results in a right manner, to say any result in the right manner. So I was fascinated by the classical results of algebraic number theory. I wanted to take them to the skies. I wanted to generalize them. And I, with my student, extended several of them. The classical results using valuation theory. They hold for many good rings. Now we have proved them for many good rings.
Ma'am, what sort of general advice would you give to those who are interested in exploring algebraic number theory and related areas? And what are the prerequisites for studying this? And what are the books which you would strongly recommend to pursue career in this area?
Algebraic number theory.
Yes.
Charity begins at home. I will ask the students to read my book because it is self-contained. It is written with a motive that you should not. Even if there's no teacher, you can learn algebraic number theory on your own. There's a set of exercises, and there are elaborate hints at the end for each difficult exercise, and there are small hints for easier exercises, and there are answers for all exercises. So that is written with the motive that students learn on their own, even if somewhere this facility of having a course in formal course in algebraic number theory is not available, but they should have prerequisite in algebra, and to enjoy it they should know basic number theory of Nyman standard, or they should know basic number theory results like quadratic reciprocity law or quadratic residues. They should know, and something congruencies, Chinese remainder theorem. No.
Ma'am, do you think there are some challenges in the mathematics education scenario in India faced by teachers as well as the students? And what, according to you, are the major challenges? And how do you address those challenges? And what is your suggestion?
I think there are many challenges. First of all, I will begin at the school level. I will say private schools. In private schools, unfortunately, the students' interest towards mathematics is always stems at the primary stage. It always takes birth at the primary level. Okay, at the school level. I will say at the school level. You must have heard about Mariam Mirza Khani. Women were not in Iran were not allowed to participate in the international math Olympiads, but it was their principal who gave them special coaching and so they were able to participate in the international math Olympiad. So teachers have a great role to play, especially mathematics teacher, because as Euclid has said, there's no royal road to geometry. I will say there's no royal road to mathematics. Teachers have a great role to play. Unfortunately, in most private schools, teachers are low paid. They're very low paid. Only a week back, I was traveling by taxi to IISER Mohali, and the young man driving the taxi, he spoke very good English and was very cultured in manners. So I asked him, what's your educational qualification and where do you belong to? He told me, I am from Firozpur in Punjab and I am MA in mathematics. And then looking, I was so happy. Sir, are you MA in mathematics? He says, yes, I am first class MA in mathematics. Said, where did you pass? He says, Dev Samaj College, Firozpur. I said, I inspected your college. It's a very good college. Such and such was the principal of your college in such and such year. He says, yes, you are right. I said, why are you driving a taxi now? He says, I worked in 2 private schools. I worked in 2 private schools. They make me work so much. At the same time, the salary they pay is so low. I said, how come other teachers are working? He says, other teachers are lady teachers. I was the only gent teacher. I have to support my parents. They have their partners, their husbands working. So whatever money they get, they think it's all right. But for me, that is not the case. Says I had to leave that job. He says I have already passed qualified 2 tests for getting a government job in a higher secondary school in Punjab. I have already qualified, and the third test I am applying the taxi and also preparing for it. It gives me time and money. Taxi applying gives me time and money to prepare for the new test also. So I really felt very heartened by it. See, the hardworking, intelligent person, how difficult it is to get a government job. And 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 our students need good teachers. Mathematics needs to be taught by good, dedicated teachers. So if they are paid so less that they think it better to apply a taxi, obey a taxi on the roads, then what will be the future of the students? Tell me. And at the college level, I am sorry to say, hardly any college or school is teaching NCERT books. Students are getting themselves registered in some dummy schools, students of 11th and 12th class, because I know several of our relatives' children, they are getting themselves registered in dummy schools. They are all the time studying tuitions, and in tuitions, they are just like technicians. They are teaching them how to solve a problem. Why this is the method to solve the problem, they won't know. The tutors, the teaching shops will not tell them why this is the method to solve it. They will only tell them this is the method to solve them, and then they want them to go through some IIT JE exam and answer in yes or no, or tick the correct answer. Out of 5, they have to tick the correct answer, so they can approximate which will be the correct answer. So that is the situation in high school, 11th and 12th. Then those who are brilliant enough to go over to good rank in JEE, they reach institutions like IISER or IITs. There, of course, one thing I will say also on behalf of teachers, the teachers nowadays have become more professional. In our time, we were told that teaching is not a profession. It is a service to mankind. It is a service to mankind. It is more a mission. That is why in earlier times when we were young, there used to be a school called Missionary School in Ambala city, and their nuns used to teach their students because they had a mission to teach. So we were told when we were young that teaching was not a profession, it was a mission. Nowadays, teaching is more a profession than a mission. The interaction between students and teachers is declining. Unfortunately, it is declining. I will say it's on the declining state. There is hardly interaction between students and teachers. And third, I will say, if students, the excessive use of modern gadgets. One student came to me. He asked me, "Madam, I want to write a MS thesis with you." I said, "Okay. Which subject are you studying?" He told me commutative algebra. I said, "Which book your teacher is following?" He did not remember the name of the book. I said, "Okay, you open your register. You open your register, and you must have noted there." He says, "Madam, I don't have a register. I write everything in iPad." I said, "Sorry, it is impossible for you to learn mathematics, to imbibe mathematics. You can pass an exam in mathematics, but you cannot learn mathematics. For mathematics, you have to do exercises with hands. You have to write down notes with hands. You may look up at your iPad, you may download a book and look at certain proof, certain exercise in the iPad, but you cannot learn mathematics by pressing your finger on an iPad or a laptop. You have to do exercises, you have to write down notes." I said, "Sorry, if you are not used to writing notes, I cannot guide you for a MSc thesis. Look for some other teacher." So this is the excessive use of gadgets, the prosperity students have got. The parents of course give them all these gadgets so that it helps them to improve their skills. But then it is the students who have to use these gadgets wisely so that they prove to be a boon for them. That's all I have to say.
Ma'am, the next question is, so if a student wants to learn or self-learn a topic in mathematics, how he or she can do that? Like, what is the strategy they should follow to self-learn a topic in mathematics?
They should have a passion for it, first of all. Strategy will automatically come. Strategy will automatically come. Some people, first of all, begin by listening to YouTube lecture. है ना? कईयों को YouTube lecture अच्छे लगते हैं. Some good YouTube lectures are there. Then there are books, then there are lecture notes. And one always keeps on learning. Like I learned from my younger colleague about that book of Ross Hansberger. I didn't know about it. I didn't know about those 3 books, Gems of Mathematics, because and one always learns something from others. One always learns something from others. So there's no a fixed path to it. Everybody has a different capacity to learn, and of course there are lots of books, but book reading is a must, because when you are reading the book, you are flipping the pages back and forth, you learn many things. But I tell the students, please don't use a laptop to learn my subject. I will never, in my since when I was a teacher, when I taught, the last class I taught was, I think, 2012. I never let students open a laptop in the class or iPad in the class. They will all write down notes, whatever I wrote on the blackboard. They will all write down notes. And if I wrote something incomplete, I told them this is incomplete, you have to solve it and complete it. And approximately it will need so many lines. You can leave those lines. So that's all I will say.
My last question is,
what advice do you give to the students pursuing the career in mathematics and research?
I will say that if they want to do research, if they have a passion for research, only then they should go for it. If they have a passion for money, they should go to IT. No, it's different. Like my own son, like I have two sons. One has a passion for money. He has gone to US. So, and he's perform and one he has a passion for both. So off and on, I keep on telling him that you should write a research paper. Money is not everything. Keep on writing new research paper. Keep on interacting with others. But they chose their own path. They are both medical professionals. They chose their own path. They're disjoint from me. They're disjoint from me. But the only thing in common is that that research paper. I write research paper in and whenever I write a research paper, I show it to them. See, I've written a research paper, so that they also feel inspired to write something. And they have to follow their own passion. But if somebody likes number theory, he or she should adopt number theory. If somebody likes data science, he or she should go for it. Somebody likes computer science, he or she should go for it. One has to follow one's passion. Had I been in statistics, I would have been a clerk or a probationary, retired as a probationary officer, or a bank of manager in a bank. So there is a difference. There's always a difference between following one's passion and following others. दूसरे लोगों की तरफ कि वो वहां जा रहा है, मुझे वहां जाना है, उससे कोई फायदा नहीं है ना. पर जब अपनी पैशन को तो फिर परस्यू भी तो करना पड़ता है ना. उसके लिए खून पसीना भी तो एक करना पड़ता है, नहीं? और फिर जब रास्ते में चलते हैं तो कारवां बढ़ता ही जाता है, कोई ना कोई मिलता ही जाता है, नहीं? कोई ना कोई अच्छा इंसान जुड़ता ही जाता है, चाहे वो फ्रेंड्स हैं, चाहे कंपेनियंस हैं, चाहे टीचर्स हैं, है ना, चाहे मेंटर्स हैं, मिलते ही जाते हैं, नहीं?
Yes, sir.
Thank you, ma'am. Thanks a lot for agreeing to join us today and give this wonderful talk and this interview. Yeah. Prapti, over to you.
Yes, ma'am. Thank you so much, ma'am, for engaging with
Thank
us
you, Prabhu.
and giving your valuable advice and valuable time. Thank you, ma'am.
Thank you, Betty. Thank you.
Okay, I'll stop the recording
Sure.
and the